I had quite a few questions from people about series convergence, and I wanted to take some time out and carefully look at a few of these because most of these fall into the same category. I'm pretty sure these are all topics we did last year, but there are a couple of series relationships that you may have forgotten from last year, and we kind of glossed over these in class because we were in a hurry trying to get to everything before school was canceled. So take a look at this first one here. Question 8. Remember, the idea here in this section is implying that most of these are geometric series. So you could list out a couple of terms, and I think you would start to see what was happening here. If n is equal to 1, you've got e squared. If n is equal to 2, you've got e to the 4th. If n is equal to 3, you've got e to the 6th, and so on. And hopefully you can see each time the numerator is being multiplied by 1, the denominator is being multiplied by e squared, okay? 1 over e squared is less than 1, okay? So this is a convergent geometric series, okay? You can just go ahead and say, hey, this thing is convergent. That's one way to approach this. The other way to approach it is to write it. This is the same thing as 1 over e squared to the n power, right? Because 1 to the n power is always going to be 1. And e squared to the n power is the same thing as e to the 2n. And then you can see that you're constantly multiplying by 1 over e squared. And again, it makes it pretty easy to see that it's a convergent geometric series. Okay? The second example here, something that, again, pretty sure we talked about last year, but we've glossed over a little bit in the lessons this year, is the idea that, remember, we've got all these rules for derivatives and integrals that allow us to take a sum or a difference and break them up into separate derivatives or separate integrals. That all goes back to summation rules from early in the year and limit rules that we worked with. And anyway, so this is the same thing as the sum of this series plus the sum of this series. And let me see if I can adjust that just slightly. So this is really the same thing as that, okay? And also, just like with derivatives, remember that you can divide a constant out of terms of a series. And so if you need to divide this 2 out front, you can bring that 2 out in front. Anyway, long story short, we're consistently multiplying by 0.1, okay? And again, if you need to list out terms, you'd have 1/10, you'd have 1/100th, 1,000th, and so on. This is a convergent series multiplied by 2. That's still going to converge, okay? Meanwhile, this series is geometric. We're constantly multiplying by 0.2. 0.2 is less than 1. This one is also going to converge. So if I have 2 convergent series, the overall sums are going to converge. And again, check the assignment. They may ask you to find the sums as well. This one up here, of course, is just going to be a geometric series with a first term of 1 over e squared and then a common difference of 1 over e squared. And you can substitute that in the formula and find the sum if you need to do that. I forgot if it asked you to do that or not. Same kind of thing here. This will be a geometric series with an r value of 1/10. Be careful and make sure you multiply by 2 at the end. But anyway, I'll let you find those sums. Let's keep going with these. 17. One of the things that maybe I didn't stress as much as I should have in the geometric series section, but I'll continue to stress moving forward. Make sure the individual terms are approaching 0, okay? So it was pretty easy for us to see that these were geometric series and that the multiplier was something less than 1. But always check the nth term, okay? This is messy. It doesn't have exponents like geometric series. I don't think on the surface it looks like it's going to be a geometric series, quite frankly, okay? But make sure you apply the nth term test. Okay, the nth term test says, hey, as n goes to infinity, are the individual terms going to approach 0? Because if they approach something else, we're just going to keep adding that thing on over and over and over again to infinity. It's not going to converge, okay? So before you do anything else, especially if it doesn't look geometric, and that's all we know how to deal with right now, check the nth term, okay? And remember, you're really looking at this, at the limit as n approaches infinity, okay? You've got n on top. that 1 is getting overpowered by that n squared. Okay, you've got radical n squared in the bottom. And anyway, n values are going to be positive here. So this square root's the primary square root. But if you notice, we're going from 1 to infinity. So these will also always be positive. So again, we're just going to end up with n over n, essentially, because n is always going to be positive here. And the limit's going to approach 1. So the point here is, as you go farther and farther out, regardless of what those terms are doing, the individual terms are approaching 1, and that means that series is not going to converge, okay? It fails the nth term test. Now again, be careful with the nth term test. Just because the individual terms approach 0 doesn't mean it converges. You would then need to go check something else. But if the individual terms don't approach 0, you're done, okay? It's a divergent series, and that's what's happening here on 17, okay? Let's go over here and look at 18. 18, again, we've got a sum. You can really break this up into 2 separate integrals, so let's do that. That's 2 over 3 to the n minus 1, and I'm doing the sum from n equals 1 to infinity. No, we aren't adding these, yeah. Anyway, this one you should be able to rewrite. You could rewrite this as, for example, that's a first power there, right? So you could write this as 1/2 to the n minus 1 power. Okay, that's not going to affect the 1. And I think you can see here that's a geometric series. You're constantly multiplying by 1/2. Now be careful, the first term here in this series, if you're trying to find the sum, would actually be 1, because anything to the 0 power would be 1. And then you'd be dividing by 1/2. So I think this would actually add up to 2. I'm doing that right off the top of my head. Okay, now this one over here, you have to be careful. I don't want to take 2 to the n minus 1 power, because that would that would kind of change things a little bit. So you can factor the 2 out, and you can factor the 2 out entirely, or you can factor it out in front like this and write that as 1 over 3 to the n minus 1. Then you can take that 1 to the n minus 1 power, and that's totally okay. And so what you're going to end up with here is the classic setup. Remember, your standard geometric series is a sub 1 times r to the n minus 1. That's kind of the typical setup. And so here we've got that. You can see we've got a constant multiplier here of 1/3. I hope I'm not off the screen, but anyway, constant multiplier here of 1/3. 1/3 is less than 1. So this is also going to converge. It's a geometric series with the first term of 2. If you substitute 1 into here, this will just be 1. And your common ratio is 1/3. And so I think that's going to end up being something like 4. Well, anyway, you can substitute that into the formula and find the sum, and we already did that one. So anyway, both of these are going to converge, so that'll be convergent, and if you need to find the sum, you can do that. The last one, going back to Algebra 1, we know if you have a sum or difference in the numerator of a fraction, you can break it up into 2 separate fractions. So I would write this as 3 to the n over 6 to the n plus, and then I would do a sum from 1 to infinity of 2 to the n over 6 to the n, okay? And notice, again, this is really the same thing as 3/6 to the n power, or 1/2 to the n power, constantly multiplying by 1/2. So that is going to be a convergent part of your series. And this one over here is the same thing as 2/6 raised to the n power. 2/6, of course, is 1/3. That's less than 1. That's also going to be convergent. So again, if you need the overall sum here, your first term would end up being 1/2. Your common difference would also be 1/2. So I think that sum would end up being 1. Over here, because n it starts out at 1, your first term would be 1/3, and then your common difference is 1/3, and you can put that in the formula and find that sum as well. So this one is a convergent series plus a convergent series will end up giving you a convergent series. And because they're geometric, you can also find the sums.